Okay, we are ready for biochemistry video number 3, which is going to be all about lipids. And I actually want to go up here for a second and finish off a couple things that I didn't mention in the carbohydrates. So, digesting starch versus cellulose. We definitely talked about it's easier for animals to digest starch than it is cellulose, and I wanted to give you a couple reasons why. Starch tends to be very easy to digest because if you look at the arrangement, every glucose is what I would call right side up. They are, all their oxygens line up in this way. And they are what we call an alpha, beta, they are the alpha version. They're an alpha glucose. Beta glucose is what cellulose is. And what that means, a beta has its OH group off of the first carbon go up instead of down. So if I draw a glucose molecule quick here. There's my glucose. This is carbon 1. Off of carbon 1, I know I have an H and I know I have an OH. So if the hydrogen angles up and the hydroxide angles down, this is an alpha glucose. If instead it went like this, where the carbon 1, the OH angles up and the hydrogen angles down, that is a beta. And the difference that it makes is when it forms that glycosidic linkage during dehydration synthesis and it's bonding to link two of these glucose molecules together, when the betas connect, it ends up looking right side up, upside down, right side up, upside down. And that is an easy way to look at a diagram of a polysaccharide and notice if it's an alpha polymer or a beta polymer. The beta polymers tend to branch more and they tend to be more difficult to digest. They need a different enzyme to actually break down that glycosidic linkage. So I hadn't mentioned that. I wanted to mention that. This just shows cellulose. It's in every single plant cell wall, so it's the most abundant, and here you can really see the branching that exists. So the polymer is the long chain, and then it actually forms these branches, and the branches make it even tougher to break down. Chitin, I just wanted to show you a picture because you're going to see a lot of structures in class. So the thing that we notice about chitin, the N at the end represents, there's a nitrogen. It doesn't represent, it makes it easier to remember. Chitin has nitrogen in it, helping it be very, very strong. And that's, we talked about the exoskeleton. All right, now we're ready to talk about lipids. So lipids are fats. So when we talk about fats, we still have carbon, hydrogen, and oxygen. So they are an organic macromolecule, large molecule. The ratio is not 1 to 2 to 1. There are carbons, lots of hydrogens, and very, very, very few oxygens. The oxygens tend to be at the ends of the molecule. So for example, a fatty acid, I hope you remember back we talked a little bit about functional groups. An acid has a carboxyl group at the end of it, and that has 2 oxygens. So very few oxygens compared to carbons and hydrogens. Most of the chain is just C's. Lipids tend to be long carbon chains, long hydrocarbon chains. There are 3 types that we're going to talk about today: triglycerides, phospholipids, and steroids. An interesting thing about lipids, they don't form polymers. So when we talked about carbs, we talked about polysaccharides and how they will link together individual glucose molecules to make a polymer, a long chain of something. These do not hook together to make long chains. They do hook together to make certain fats, but not long chains, not polymers, not repeating units. All right, structure. Glycerol is a 3-carbon alcohol, so I want you to draw glycerol. It looks like this. Carbon, carbon, carbon. Each carbon gets an OH, 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 and the rest of the bonds are all hydrogens. That is the structure of glycerol. Fatty acid is a long hydrocarbon chain that at the end it has a carboxyl group. And remember, a carboxyl group looks like this, double bonded O and an OH. It's considered an acid because it will drop that hydrogen, be negative itself, and if you add hydrogen to a solution, you are acting as an acid because you are increasing the hydrogen ion concentration. So, to build a triglyceride, we would have to add 1, 2, 3 fatty acid chains to the glycerol. So I'm going to do that with you right now so that you can draw it right in your notes. I am going to have my carboxyl group right here. And then I'm just going to go like this and put C, 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 dot, dot, dot. Keeps going. Ends in a carbon that just has 3 hydrogens around it. Could be a very long chain. Now, how would these connect? Right now there's no space, no opening for a bond, so we have to dehydrate it. Whenever you're synthesizing and building something larger, you need to dehydrate. So I'm going to take the red pen here and show you the removal of water. This is going to come out, forming H2O. So if I do this 3 times, I will produce 3 waters in the process. I now have an opening. This oxygen can bond right here to this carbon. So now that I've shown it one time with that, I am going to erase this H and erase this H and draw in what it would look like. I have my carbon. It has a double bonded oxygen, and then the rest of my carbon chain. And over here, same thing. Carbon with a double bonded O that used to be a carboxyl group, but it lost its OH. And then my carbon, dot, dot, dot. When we talked about carbs, we talked about a glycosidic linkage. Glyco makes you think sugar. This is actually called an ester linkage because an ester is a functional group with a carbon with a double bonded O and then an oxygen somewhere in the middle of my carbon chain. So circle this and put this as an ester linkage. Right, so this was formed by dehydration synthesis. I have 1 glycerol and I have 3 fatty acid chains attached. The addition of each fatty acid chain resulted in the removal of 1 water. Here's another picture, just sort of their diagram of it. Here is my ester linkage. So there it is, just like we drew it, between the OH group that was dropped and this carboxyl. So the carboxyl group had an OH, this O had an H because it was an alcohol, removed it as water, formed that linkage. All right, so what are fats for? They store energy for your body because there's so many bonds. Bonds are potential energy just waiting to be used. So it's very concentrated because it's all H's and C's. And I related it back to food here. When you think about your food and what you intake in a day, when you intake fat calories, there's actually more than twice as many calories in a gram of fat versus a gram of sugar. And the reason why is there's more potential energy in that bond because it's just a long hydrocarbon chain. What else are they for? Cushioning organs. Each organ tends to, especially heart, has that special layer of insulation around it. And insulating your body. So all of your cells actually have lipids within the cell membranes. Helps keep water out of our body as well. All right, we got to talk about the types of fatty acids. So fatty acids were the long chain with a carboxyl at the end. If it is a saturated fat, S for saturated, S for straight chain, S for solid at room temperature. So the last S I want to put here, all single bonds. Single carbon-carbon bonds. So S for saturated, S for straight, S for solid at room temperature, S for single, and then I like to add my own, my little Mancuso one, S for stay away. Saturated fats are not good for you. They are actually so straight in their structure that they will be a solid at room temperature, which means that they are the ones that tend to clog your arteries and your veins. They are not good for your heart. They are the #1 cause of heart attacks is you have too much saturated fats in your diet. So I want you to picture it like all of these straight chains in a row do not lead to flexibility. So our next type will give us some flexibility. Unsaturated fats are less likely to clump up and cause problems for your blood vessels because there's more spacing. they are more flexible. So in unsaturated fat, look at the difference in these chains. There are kinks in the chains. A kink represents a double bond in the fatty acid chain. So plants, fish fats, olive oil, peanuts, all of those have a good amount of unsaturated fats, which are much healthier for you. They also are going to be a liquid at room temperature because there's more flexibility in their structure. The kinks are made by double bonded carbons to prevent the molecules from packing too tightly together. When you eat too many saturated fats, you have too much of that clumping, and that causes a problem. So I took a little image here of our garbage plate from Nick Tahoe's. If you let a garbage plate sit, it will actually solidify. And the solidifying is those saturated fats at room temperature. When they cool down, they become a solid. So this is showing that there's a lot of saturated fats involved. These, the fats within them, tend to be liquids and are much healthier because they have the kinks in their tails and they allow more flexibility. All right, one of the most important lipids that we will study all year are phospholipids because they make up cell membranes. Every cell has phospholipids in it. This time it's a glycerol, but only 2 fatty acid chains and a phosphate group. So here is our glycerol. 2 of the OHs went to form that ester linkage, so we have 2 fatty acid chains. The 3rd OH attached a phosphate group, PO4. And that phosphate group is very negative, and it allows the property of the phospholipid to be multi-talented. There is a region here that is negative, and there's a region here that is very uncharged. Fats, because they are just chains of C's and H's, tend to be very non-polar. That is polar. So this molecule has a polar section and a non-polar section. I also expect when you look at this picture, you notice right away, ooh, this one is unsaturated because it has a kink in the tail, and this is a saturated fatty acid tail. This part right here was my glycerol. I am going to be giving you diagrams in class so that you can go through and identify things and really notice structures, and not just what they are, but because of their structure, what will they be able to do in your body. All right, next one. The fatty acid tails are hydrophobic. We started talking about this word in class. Hydro, water, phobic, fearing. So they fear water. They are non-polar. The phosphate head is very hydrophilic because it has charges. That makes it polar. That makes it attracted to water. We call this amphipathic, the fact that it has both traits. One region of the molecule likes water. One region of the molecule does not like water. This tends to be polar. This tends to be non-polar. That will cause it to arrange itself in a very specific way. If you take phospholipids and put them in water, they will actually arrange themselves into a circle, with the tails all facing in away from the water, and the heads where the phosphate groups were, where it was very negative, facing out towards the water because they are hydrophilic. Now, over time, it is noticed that membranes have formed within, like you could literally put a droplet of phospholipids in water and this would happen, but membranes have formed over the course of time, billions of years. So the way that a phospholipid is arranged in a cell membrane is that it is a lipid bilayer. Bilayer. And you can see the 2 layers here. The heads face the outside of the cell, the heads face the inside of the cell because it's a water environment. So the part that's hydrophilic is going to face the water. The tails orient themselves towards each other because this is very non-polar. That does not want to be near the water. It is hydrophobic. So that is why a cell membrane arranges itself in a bilayer. All right, why is this important? So if we have a barrier, we can now keep water on one side and on the other side and have a selectively permeable membrane that will only allow certain things through at certain times. So it defines the outside versus the inside, and makes up these cell membranes and their barriers. All right, we are moving on to the last grouping. So we had triglycerides, we had phospholipids. Our last type of fat that we're going to talk about, our last big lipid category, are steroids. Steroids have a completely different shape. So shape-wise, you will be able to notice these right away. They are almost always 4 rings. And the rings, they do not draw out every carbon, but there would be a carbon here, and a carbon here, and a carbon here, and here, and here. This line shows me there's a double bond between those 2 carbons, a carbon here, and here. So this is a large molecule. It has a lot of carbons. They form these rings, but there is not an oxygen with each one. So it is definitely not to be confused with any type of sugar, because you only see 1 oxygen in this whole molecule right now. This is cholesterol. When you look at some other things like testosterone and estrogen, you get the same basic look, but it has a slight difference in structure. So 4 fused carbon rings, different steroids created by attaching different functional groups to the rings. So we're going to add a different OH here, or the CH3 is a methyl group. Different structure creates different function. That is probably one of the key things for the whole unit. Structure determines function. What can you tell me about the structure that will allow me to say what it can do? What could its job be? So cholesterol has a very specific job based on the fact that it has this OH and this methyl and this chain. Sex hormones have a different structure slightly. So cholesterol, an important thing about cholesterol is that it can actually provide a little bit more flexibility in a cell membrane as long as there's not too much of it. So that's when we say you get your cholesterol levels checked. You want a healthy amount of cholesterol so that it can be something to increase the flexibility of a cell membrane. But if you have too much of it, it could actually build up and cause a problem. Here are some other hormones. So cortisol is a steroid that you release in a time of fight or flight, like let's say you're in a car accident. It is a hormone that your body would release. So some hormones, sex hormones especially, are going to be a lipid, not a protein. Here is aldosterone, which actually helps control your water levels in your kidney. Here's testosterone, here's an estrogen, and here's progesterone. So each one has a different functional group attached, and that allows it to do its job differently. Its form determines its function. All right, I lastly have some vocab here. I think it's great to have a section of your notebook be for vocab. So fatty acids, saturated fatty acids, unsaturated, phospholipids, amphipathic, and steroids. These would be some good things to add into your notes. You may pause it there if you'd like to hold that and write those down. This is from chapters 4 and 5 in your textbook.